Hello friends, good morning to all of you. Again, welcome back to LNT College Multimedia Studio, Muzaffarpur. Today I am entitled to focus on the oxides, peroxides and hydroxides of alkaline earth metals. So what type of chemistry and reactions are involved in the oxides and peroxides and hydroxides? Basically, we are trying to focus on these topics, right? So as you know that in case of uh, oxides, peroxides and hydroxides, the negative anion, so that is oxide means O2 minus negative charge, and that is actually not superoxide, it is actually peroxides, right? So what is the structure formula of peroxides? That is O2 2 minus, and hydroxides, that is mononegatively charged OH minus, that is hydroxide ion. So these are the anionic species, uh, and they are supposed to form ionic compounds with alkaline earth metal in a divalent cationic form, right? Now what will be the stability of oxides, peroxides and hydroxides? That will be decided by their stability in reference to lattice energy and hydration energy, right? So students, first we will focus on the chemistry of the alkaline earth metals little bit, and then we will correlate with the nature of the bonds to establish a lattice energy and hydration energy and Lewis acid base interactions. And after studying these three parameters, we will be we will be able to explain the behavior of solubilities in particular group, and the thermal stability and reactivities. So these are the things that we are trying to focus and correlate with these parameters, right? So as you know that all the alkaline earth metals actually, because of the low negative standard reduction potentials and low ionization energy, and most important, that is high electropositive characters, so they tends to lose their two valence electrons to form a bivalent cation, so that is M2 plus, right? So this M2 plus actually stands for beryllium 2 plus, magnesium 2 plus and calcium 2 plus, and similarly strontium 2 plus and barium 2 plus. So depending on the stability of and structure of the these bivalent cations, and they form the ionic compounds. So mostly all these species are responsible to form ionic compounds because of high electropositive characters. So they can interact with negatively charged anions, right, via electrostatic interactions. So first thing is that you know that beryllium is the topmost metal of alkaline earth metals. So Be2 plus actually this is most and highly hydrated species, and it remain always in the form of BeH2O का whole fries 2 plus, that is tetra aqua berylate ion or beryllium ions. So uh, what is the actually heat of hydration, or simply you can say enthalpy of hydration for this particular beryllium 2 plus? So it will release much more energy, that is minus 2994 kilojoule per mole. So this is the enthalpy of hydration, that is more negatively negative value, so which confirms that beryllium does not exist as beryllium 2 plus, rather it exists as beryllium which is hydrated, or you simply say that BeH2O ka whole price and 2 plus, right? So this is the beauty of this beryllium 2 plus. And most of the beryllium 2 plus compounds, they are not purely ionic, rather it forms a covalent compounds. So because of the polarization effect as per the Fajan's rule, and hence you can say that beryllium 2 plus actually has a highly and small charged cationic species, so they can form compounds with negatively charged species through electrostatic interactions. But so because of the polarization effect of this small and highly charged beryllium 2 plus, so the anions are supposed to be polarized, and hence there is some sort of covalent characters in this particular beryllium compounds. So most of the beryllium 2 plus forms covalent compounds like beryllium oxides or beryllium hydroxides. So any of the compounds that forms through the combination of the cation anions, in case of beryllium, they form covalent ionic compounds, right? So what is the actually all these metals actually react with oxygen directly and burns in the atmosphere. So it form oxide compounds. So that is actually MO, right? So this MO is what metal exists as 2 plus and oxygen exists at 2 negative charge. So if you think on the Kapuscinski equation, the Kapuscinski equation gives us idea about the enthalpy of lattice, or you can simply say lattice enthalpy, when only we have a ionic ready data are available. So in case of these metals, we have already known that this M2 plus, that is actually M2 plus, in this particular series from moving top to bottom, the ionic radius increases, right? And the least and most small sized cation M is, that is beryllium 2 plus. And because of the small size of beryllium 2 plus and small size of oxide ion, they form a very strong lattice. So that is metal oxide, that is beryllium oxide, right? Beryllium oxide. So this is a covalent compound. Actually, this is not ionic because of the polarization effect of beryllium 2 plus, right? So rest of the other metals similarly burns in the atmosphere of oxygen and directly react with that particular oxygen to form magnesium oxide, calcium oxide, and strontium oxide and barium oxides. So these are the oxides compound that forms actually in the presence of oxygen of the atmosphere, right? And the stability actually depends on the various factors like lattice structure and lattice energy. So as in case of beryllium oxide, so because of here as per Kapuscinski equation, you know that delta H L is directly proportional to Z plus, Z minus, and it is inversely proportional to R plus, R minus, right? So larger the product of charges on particular this lattice, higher will be lattice enthalpy. And if interionic distance is small between cation and anion, then the lattice enthalpy will be very, very high, right? So in case of beryllium oxides, what actually is analyzed here, beryllium 2 plus and oxide 2 minus. So it has very small interionic distance between these two ions. So naturally it forms more lattice energy. compounds, that is beryllium oxide, and here 2 plus 2 plus 2 minus, the product is 4. It means it has 4 times higher lattice energy than that of the group first alkali metal oxides compounds. So they are more stable, and because of the but in general, because of the high lattice energy, it should be most stable. But here beryllium actually exists as hydrated ion. So and this beryllium 2 plus is highly and small charge cation, so they polarize the electronic cloud of Be bond O, and the stability decreases because of the covalent characters. So these compounds are actually not very good stable at ambient temperature. Rather they are rather they are decomposed or highly reactive. So this beryllium oxide is actually amphoteric in nature, so they can react with acid as well as base. So once they react with acid, it forms salts like BeO, then react with HCl, then it forms beryllium chloride, right? And once they react with base, that is sodium hydroxide, then it forms beryllium hydroxide, right? So once they react with sodium hydroxide, right, so it forms BeOH ka whole twice, that is beryllium hydroxide, right? And more important thing is that this is actually because of the amphoteric characteristics, so it can react with HCl as well as base, so they are not as much stable as rest of the oxides in the particular series. Okay, so once we talk on the these metals, so that is magnesium, calcium, strontium and barium. So magnesium naturally little larger compared to beryllium, and so it also forms a oxide compounds in the presence of actually oxygen. So actually this is magnesium oxides and calcium oxides and strontium oxide and barium oxides. In case of magnesium oxide, it has highest lattice enthalpy minus 3923 kilojoule per mole, right? And the lattice energy for barium compounds, that is barium oxide, in case of barium oxide, that is minus 3120. It means lattice energy decreases in this particular series. So barium compounds, it means barium oxides are not as much as stable as magnesium oxides, right? So because of the high lattice energy, magnesium oxides are supposed to be highly stable compared to the barium oxides because of differences in this lattice energy value, right? So what happens actually is that because of the lattice enthalpy, here beryllium 2 plus is hard metal cation, hard, and oxide 2 minus is also hard in nature. So hard interactions actually favors the formation of most stable compounds. So beryllium, magnesium and calcium, actually they are hard metal cations in a cationic form, and it can react with hard anions. So that is oxide ions, that is your oxide ions, hydroxide ions. So these are the fluoride ions. These are the hard Lewis base. They are called hard Lewis base, and always these ions preferred to react with hard metal cations, right? So and as you move from magnesium to barium, hardness decreases little bit, and this is because of the increased size effect. And there is a percentage of softness in this series. So soft metals can't react strongly with hard Lewis bases, and the resultant compounds, that is oxide, fluorides, hydroxides, will be little less stable, right? So they can undergo thermal decompositions. So this is the beauty of the reactions and chemistry of these alkaline metals and metal ions, right? So what happens in a particular conditions, so that is actually metal in a solid forms, they directly react with the ignition of the oxygen in the atmosphere to form metal oxides, right? So this is MO. M stands for all alkaline earth metals. So this is the actually metal oxides. And once these metal oxides actually react with excess of the oxygens, then it at a high temperature, right? So this metal oxide, if it react with oxygen at high temperature, then it forms a metal peroxides. The formula of metal peroxides look like that, that is MO2, right? And this contains M 2 plus and O2 2 minus. Here 2 plus charge and on the metal and 2 negative charge on the peroxide ion. It means here also the product of charges is 2 multiplied 2, that is 4 times higher lattice enthalpy than that of the group first alkali metal superoxides. So actually alkaline earth metal peroxides are highly stable because of the high lattice energy compared to the group first alkali metal peroxides. And naturally, because of the size of the bivalent cation is smaller compared to the monovalent group first alkali metal, right? So lesser interionic distance favors larger lattice energy value. But what happens actually here, if this reaction in a series actually happens, now the metal peroxides is supposed to be decomposed, right? And depending on the bond between this metal and peroxide ion, so the extent of decomposition varies, and which requires high temperature or low temperatures. So in general, metal peroxides undergo decomposition to form again metal oxides as a solid mass product plus half O2 gas, and hence this reaction is most important because of the liberation of the oxygen gas in the atmosphere, which will be reused by human beings on that particular planet. So what are the chances and probability of thermal decomposition of this peroxide into oxides? So that will depends on the lattice enthalpy of these two particular oxide and peroxide compounds. So peroxides have little, as you know that in case of oxide and O2 minus, the size of this O2 minus is smaller compared to peroxide ion. So peroxide ion is naturally larger compared to oxide ion, and hence metal peroxides have little larger interionic distance. So larger interionic distance indicates little lower lattice enthalpy and compared to the particular metal oxides, and metal oxides have little lower interionic distance, so it has naturally high lattice enthalpy. So metal oxides have larger lattice enthalpy uh, to that of metal peroxides. So, what is the chance of existence of this particular thermal decomposition? If this product remains stable in this product side, it means it has very high lattice enthalpy, so they can exist in the nature. But if the lattice enthalpy of this is low, very low compared to this peroxide ion, then this product is not stable, and the hence peroxide compound is highly stable and they require high temperature to decompose. Okay, so here we have shown a example with an example how the stability of peroxides increases in this particular group of alkaline earth metal peroxides. So what is here beauty is that since beryllium peroxides are naturally because of hydrated beryllium 2 plus, so exact lattice enthalpy is not estimated here. So because of the formation of the covalent ionic compounds, so here we have taken 4 peroxides, that is magnesium peroxides, calcium peroxide, and strontium peroxide, and barium peroxides. In general, all these peroxide actually thermally decompose to form metal oxides, right? So how the chances and probability of the particular metal oxides increases or decreases in this group, so that can be understood through the calculation of difference of lattice enthalpy between these two oxides and peroxides, right? So in case of magnesium peroxides, the lattice enthalpy, that is 3315 kilojoule per mole, right? So that is actually estimated through Kapuscinski equation, where we have a ionic radii that is known for magnesium 2 plus and peroxide O2 2 minus. So in case of oxide, actually it is 126 picometer, right? And in case of peroxide, the size 180 picometer. So peroxide ion is larger compared to oxide anion. And from the table, as in the previous lectures, we have shown that in a series from top to down, ionic radius of metal cations increases, right? So Mg2 plus is smaller compared to barium 2 plus. So barium 2 plus is the largest bivalent metal cation in this particular series, right? So if this reaction is feasible, thermodynamically feasible, then it forms magnesium oxide and through release of oxygen gas. And what is the lattice enthalpy? So that is calculated through the Kapuscinski equation, that is 4037 kilojoule per mole, right? So now I am interested to calculate the differences of lattice enthalpy between these magnesium peroxide and magnesium oxide. Then the delta H, that is lattice enthalpy. So lattice enthalpy delta H difference is equal to the difference of lattice enthalpy of magnesium oxide minus lattice enthalpy of magnesium, not magnesium oxide, sorry, this is magnesium peroxide. So lattice enthalpy of magnesium peroxide minus lattice enthalpy of magnesium oxide. The result is actually minus 722 kilojoule per mole, right? So here very high difference, that is minus 722 kilojoule per mole. In case of magnesium peroxides and oxide compounds, the differences look like that. But in this series, we are not going to consider here for the calculation of all the peroxides and oxides. Rather, the bottom metal cation, that is barium peroxide, undergo thermal decomposition to form barium oxides, right, plus oxygen gas. If this reaction happens thermodynamically, then the lattice enthalpy difference must be highly negative. But what here that from the calculation we can actually explain. The lattice enthalpy of this barium peroxide, that is 2684, right, 2684 kilojoule per moles, while in case of barium oxide it is 3147 kilojoule per mole. So what inferences can be drawn here? Actually, that is the difference of lattice enthalpy between these two compounds. So that is lattice enthalpy difference is minus 463 kilojoule per mole. It means 463 kilojoule per mole. Here minus 722 kilojoule per mole. Here the value is minus 463 kilojoule per mole. So what these value indicate? Actually, in this particular series, the formation of oxide will be only favored if the difference of lattice enthalpy will be a very, very high negative value, and then only we can illustrate the existence of this particular oxide compounds. But if the negative value decreases in this particular series, it means the stability of the particular oxide compounds are supposed to be decreased, and because of the decreased lattice enthalpy difference. So what inferences is drawn here? Magnesium peroxide is less stable compared to barium peroxide, because in case of these two compounds, here the difference of lattice enthalpy is minus 722 kilojoule per mole, and in case of this, here minus 463. So here high negative value, here low negative value. It means this compound is stable. Hence, magnesium peroxide undergo thermal decomposition and rapidly to form this particular magnesium oxide, and the lattice enthalpy difference of formation of this particular compound is minus 722 kilojoule per mole. But in case of barium peroxide, the lattice enthalpy difference is minus 463. It means the chances of existence of this particular compound, that is barium oxide, is low in this particular reaction, and hence you can say that this barium peroxide is more stable and compared to this magnesium peroxide, and because of the differences in lattice enthalpy. So this barium oxide does not decomposes uh, mm, rapidly at a ambient temperature. Uh, Rather, it requires very high temperatures so that it can be decomposed. So what actually inferences are that from moving top to bottom in this particular series, the formation of peroxides are actually increases. It means uh, most of the bottom compounds, that is calcium peroxide, strontium peroxide, barium peroxides, they are highly stable ionic compounds, and it has high stability, and it is because of the uh, stability of the peroxide anions through these particular bivalent cations. As you moving from top to bottom, you have seen that calcium 2 plus is smaller compared to strontium 2 plus, and barium 2 plus is the largest metal bivalent cation. So larger bivalent cation naturally stabilize this particular peroxide anions. So as per Fajan's rule, so the compound is actually ionic and they are most stable. So in this series, the peroxides compounds are thermodynamically stable, and if uh, if if you want to decompose it, then these compounds requires very high temperatures. So barium peroxide is the most stable peroxides in these particular compounds, right? And this peroxide compound actually is basic in characteristics, right? So all these peroxides are basics in characteristics that can react with acid to form a salt. So barium peroxide actually react with HCl, then it can forms barium chloride, and that is H2O will be released. So salt can be formed through the reaction of the peroxides, right? But in case of beryllium and magnesium, oxide compounds are stables, but in case of calcium, strontium, barium, peroxide compounds are stables, right? Now, hydroxides. What is hydroxide? The hydroxide, a compound and that contains OH minus, right? So this OH minus is hard Lewis base, hard Lewis base, right? So hard Lewis base prefer to react with hard Lewis acids. So in case of alkaline earth metal, actually beryllium 2 plus and magnesium 2 plus, right, they are much more hard as compared to rest of the bottom bivalent cations. So they mostly form to actually hydroxides because of the hard interactions. As you know that hard interactions are favored and soft interactions also favored, and this is because of the stability factor. But hard acid soft base interaction as is actually little stability, and soft acid and hard base also actually they are less stable, right? So hydroxides are actually ionic compounds. All these bivalent metal cation M2 plus form hydroxide compounds, and in general they are all ionic compounds, right, students? This is actually beryllium hydroxide, and this is your magnesium hydroxides and calcium hydroxide. This is strontium hydroxide and this is barium hydroxide, right? Here M2 plus, right, and hydroxide as -1 charge. It means they are actually exist as OH minus, right? So here 2 multiply 1, that is 2. So the lattice enthalpy of hydroxide compounds are 2 times larger compared to the group first alkali metal hydroxide. In case of alkali metal hydroxide, that is M plus OH minus 1 multiply 1. So that is only 1 times of charges here. Here 2 times of charges actually. So because of the high product of charge, the lattice enthalpy of bivalent alkaline earth metals is high, right? So higher the lattice enthalpy means they have high electrostatic interactions, right, between M2 plus and hydroxide ions, right? So if all the metal oxides, actually suppose that is your M, in case of MO, they are susceptible to react with H2O, right? So if this metal oxide react with H2O, it forms MOH ka whole twice, that is metal hydroxide, right? So beryllium oxide also forms beryllium hydroxide with the reaction of water. So in this reach beryllium hydroxide, and this is the your barium hydroxide, and this is your beryllium hydroxide, right? So beryllium hydroxide is actually less basic because of the amphoteric characteristics. So it is amphoteric hydroxides, and rest of the hydroxides like magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxides, they are basics. So actually this is weak basic, right? And calcium, strontium and barium hydroxides are strong basic. So these compounds, calcium hydroxide, strontium hydroxide, barium hydroxide, don't react with hydroxide ion in the particular reactions, and they only react with acids, right? But this beryllium hydroxide can react with acid as well as base because of the amphoteric characteristics, and magnesium hydroxides actually weak base, so because of the size of the Mg2 plus, so that is little larger compared to beryllium 2 plus. So here little covalency occurs. It means Mg bond O is little is stronger, but in case of this beryllium hydroxide, Be bond O, in case of this actually Be bond O, and here Mg bond O. So this BeO bond is stronger compared to MgO bond, and that is why the entity and the existence of pure hydroxide ion is not actually stabilized by these two ions, rather than distortion of the electronic cloud of the structure of the hydroxide ion. But in case of calcium, strontium, barium, because of the increased size effect, the hydroxide ion naturally actually they are stabilized by M2 plus cations, and favors the formation of the ionic hydroxide. So as you move from top to bottom, calcium hydroxide in the solution, they always remain Ca2 plus OH minus, and it always favors that is Sr2 plus and OH minus, and this always favors Ba2 plus and 2OH minus. So what actually here you have seen that the concentration of the hydroxide ion actually increases from calcium to barium, right? It means here the existence of both ions are possible and they can remain in the water medium. So the resultant solution appears as basic in characters. So basicity increases from top to bottom. So this is beryllium oxide is the least basic, while barium hydroxide is the most basic compounds. Most basic compounds. Now, what is the solubility of this particular hydroxides? Actually, solubility is decided by the lattice energy and hydration energy. So, what happens actually is that in case of solubility, the hydration energy, if hydration energy is high compared to lattice energy of that particular ionic compounds, then the solubility of that particular compounds will be high, because increased hydration energy favors solubility. So increased hydration energy favors solubility, right? Solubility. It means solubility of hydroxide compound, that is OMH का whole twice, is actually directly proportional to hydration energy, right? And it is inversely proportional to lattice energy. But MgOH का whole twice, and this is calcium OH का whole twice, and this is your strontium OH का whole twice. So that is your barium OH का whole twice, right? In this case, barium hydroxide, what you can expect? So here barium 2 plus and hydroxide as 1 minus, right? It has very large size. So this is less hydrated bivalent cation, right? But in this case, Mg2 plus, this is highly hydrated. And because of the covalency, the concentration of hydroxide ion is very low in the solutions. And because of the stability of the hydroxide ion through larger cations, the concentration of hydroxide ion in the solution is very, very high, right? So, low lattice energy means high solubility. In case of barium hydroxide, lattice enthalpy, lattice energy is low. Lattice energy is low because of the larger barium 2 plus and hydroxide ion. Lattice energy is low. Since solubility is directly inversely proportional to lattice energy, low lattice energy favors more solubility. So barium hydroxide is highly soluble in water and compared to magnesium hydroxide. So magnesium hydroxide, naturally it has very high hydration energy. The solubility must be very high in case of magnesium hydroxide, and but because of the covalent character in this particular compounds, so the solubility is low. So beryllium hydroxide and magnesium hydroxide, these are the compounds. Actually, they are less soluble in the water, right? But as you move from calcium, strontium, barium, these hydroxide compounds are actually much more soluble compared to the beryllium hydroxide and magnesium hydroxide. And the solubility is actually depends on the hydration energy. Higher the hydration energy, higher will be solubility in general, and lower the lattice energy, higher will be solubility. And in more general, you can that is explain delta H solution, that is equal to delta H lattice minus delta H hydration, right? If this difference is high negative, right, it means the compound will be highly soluble in this particular solvent, that is in case of water, they will be highly soluble. But if this differences is supposed to be decreased in the series, then the solubility will be decreases. But in this series, the solubility is actually decided by their lattice energy, and lattice energy is actually low for these compounds. So solubility will be very, very high. And they are most basic compounds in this series, so they can react with acids. That is actually, suppose that is this is your calcium hydroxide, this is called lime water, right? This is called lime water. So if it react with H2SO4, right, so it react with H2SO4, then it forms calcium sulfate, right? Now CO2, so and then H2O. So this is calcium sulfate, that is oxo salts, and this is also ionic compounds. So this is the beauty of hydroxides. So because of the basic character, it react with acids, that is H2SO4. And this calcium hydroxide actually are highly susceptible to react with carbon dioxide in the atmosphere. So in the atmosphere, or if it is bubbled through the excess concentration of the carbon dioxide, then the reaction takes place thermodynamically, and it forms, that is calcium carbonate, and that is H2O, and that is actually this is H2O only. So what is actually, this is your H2O. So this is calcium carbonate, which is found in the chalk, marbles, and any other stones. So this is precipitated in the solution, that is calcium carbonate. But this calcium carbonate, right, this calcium carbonate, in the presence of further CO2 plus H2O, it forms calcium CO3 का whole twice, right? This is calcium bicarbonate. So this is soluble in the water because of presence of calcium 2 plus and bicarbonate as uninegative charge. but sometimes the reaction is reversible. So again, this compound, after passing of the time, they will be converted back to this insoluble. This is your insoluble compound. So in this way, calcium hydroxide, that is lime water, so it is used to test the carbon dioxide in organic reactions and any other particular reactions or in the environment or in the atmosphere. So this is the actually beauty of hydroxides. So most of the actually compounds, hydroxide compounds, they are actually stables, and because of the existence of bivalent cation and hydroxide anion in the water, right? So what actually favors now here we have explained the covalent bond formation or formation of bond between beryllium hydroxide ions. As you know that beryllium 2 plus does not exist as free state, rather it exists as beryllium equated ion, or that is BeH2O का whole price and 2 plus. So beryllium 2 plus hydrated, that is equated, right? So they are actually, it is not stable as a B2 plus, rather it is stable in a aqueous medium as a hydrated form. So most of the beryllium salts are actually form a series of hydroxo compounds in the water medium, right? Like structure where hydroxide ion acts as a bridge between two beryllium centers. So it forms a polymeric network-like structure. Here two beryllium are interconnected through two hydroxide bridge. Here three berylliums, they are interconnected with four hydroxide bridge. So similarly, the extension structure could be obtained through the concentration. So overall, the charge of this particular compound is 2 minus, and here 2 minus. So length of the catenation increases, it still maintains 2 negative charge, because all the beryllium metals exist as plus 2 charge, right? So here plus 2 charge, here plus 2 charge, and hydroxide exists as OH minus, right? So this is your OH minus, and this OH minus is actually hard Lewis base, and all the beryllium, they are actually surrounded by 4 bonds. So all the beryllium in this particular compounds, they are sp hybrid, sp3 hybrid, right? And this they are called hydroxo compounds. This hydroxide ion actually acts as a bridge between these two centers in the above and in the similarly in the below, and so they react or they interact with these two beryllium 2 plus ions. So this type of extended polymeric structure actually once they are treated with alkali, that is sodium hydroxide, what happens, the polymeric structure are supposed to be break down, or simply you can say the extended structures are transformed into monomeric form. So it forms, that is beryllium OH whole 4 overall 2 negative charge. So in this case beryllium 2 plus. So this actually tetrahydroxy beryllium or berylate, you can simply beryllium compounds. So it has tetrahedral structure and similar to the beryllium tetraaqua compound. So this is tetrahedral, this is tetrahedral. So the similarity in the structure actually gives us idea about that the most of the beryllium 2 plus exist as BeH2O ka whole 4, and this 2 plus charge is stabilized by negative, that is actually this 2 plus, that is beryllium hydroxide 4, that is 2 minus. So that is similar to beryllium H2O whole 4, that is 2 plus, right? So most of the compounds are actually salts that occurs as BeH2O whole 4, that is SO4, or you can simply say BeH2O whole 4, that is NO3 ka whole twice. So these are the beryllium salts, and in the they remain as, that is cationic form, and this is your anionic form. Here sulfate as 2 negative charge and nitrate as NO3 1 negative charge, right? So 2 negative charge, 2 positive charge, they will be neutral, and here 2 positive charge will be stabilized by 2 nitrate ion. So these are the beryllium salts. Actually they remain in this form in the compounds. Okay, so what actually happens here, and this is the actually chemistry of oxide, peroxides and hydroxides. So all these aspects and ideas, I hope they will actually help you to understand the chemistry of peroxides and oxides and hydroxides, right? So hopefully I understand that this topic would be more exciting and energetic for your brain, and hope that this video will be comfortable and compatible to your mind, and this will help to enhance your chemistry knowledge. So please don't forget to actually share, comment and like on this particular video. So thank you students. Again I will meet you in the next video. Please keep patience.